Okay, continued. Why are swimming pools colder at the bottom? So the sun is coming in and heating it, but the reason it's colder is the same reason we just had the last one. It's because of convection. The colder, more dense water sinks to the bottom. Okay, so here we've got a phase change graph. It says what units are on the X and Y axis on this graph. So if I have an ex-boyfriend, ex-girlfriend, this is my X is down here. This is my independent variable. So this is my X. I remember this is my Y because I can draw the letter Y and it connects here. So my X-axis here says heat energy. I know that some teachers also were going as time, like as time was going on and as more heat energy was being added. The Y-axis here, it says right there, is my temperature. And because this is a study guide, I'm just going to include what does temperature mean. Temperature is the word for average kinetic energy. What is the concept behind the hot air balloon rising in the air? So we talked about this in class, that you've got a little fire here that's heating up the air, making it less dense, and so that the hot air is rising. And if I've got the hot air rising, hot air is in the air. I'm just going to, again, air, and I'm going to say air, I'm going to say gases, sorry, gases are known as fluids. Gases and liquids are fluids. So that is convection. Okay, what does the brown and red arrow demonstrate? So my copy here, oops, sorry, not very clear, so I'm going to label all of it. So here is, this is melting, and I think if you look on yours, it's, yeah. So that looks like the brown arrow is melting, and that this is the red arrow on the paper, and this is vaporization. Those are also indications of a phase change. And the reason I know that's a phase change is it's going from a solid, this is your phase change, and it's turning into a liquid. Vaporization, you've got your liquid, it's vaporizing, this is your phase change here, and it's turning into a gas. Why is the graph flat in some places? That's your melting and vaporization. And that is my phase change. What phase change happens when a solid becomes a liquid? That phase change is melting. Here we have another phase change graph. Identify the phases of matter at various points. So A, this is going to be, if I look even up here, I can tell it's a solid. So A is a solid. If I'm going as if I'm adding energy here, B is going to be, it's melting. C is a liquid, and the temperature is rising. It's a liquid here, temperature is rising, and then here it is another flat line. So then it's going to be a vapor. And then once it hits this point here, it turns into a gas. So here's my solid, my liquid, and my gas. And these flat lines are my phase changes. And if I were taking energy away, those would be different. It still would be a solid, a liquid, and a gas, but instead of melting, it would be condensing, or freezing, and this would be condensing. Okay, so here we've got 3 thermometers. This is the Kelvin scale, the Celsius scale, the Fahrenheit scale. Looking at the temperatures above, state the freezing point of water in degrees Celsius. So if I look here, I know that 0 degrees is Celsius for freezing point. So the freezing point of water, if I know that this is here, and I look over, and it's 273 Kelvin. So I also know that if I'm converting, I could use this and just add 273. So here it says normal body temperature. Normal body temperature in Fahrenheit is 98.6 degrees Fahrenheit. And in Kelvin, just all I need to do is go across. It'd be 37 if it were Celsius, but they're asking what it would be in Kelvin, 310. So on the test, you do not need to know how to convert at all Fahrenheit to Kelvin. Honors and AAP will need to know how to convert from Celsius to Kelvin. And just know that if you're going Celsius to Kelvin, you're just adding 273. So here you have 100 degrees Celsius, you add 273, it would equal 373 Kelvin. If you're given Kelvin and you need to convert to Celsius, you're just subtracting. So absolute 0 is temperature at which all molecular motion stops. No movement at all. Give examples of 2 heat conductors and 2 examples of heat insulators. So a heat conductor, I'm looking up my pictures online to see if I can see, would be, like they've got examples, 2 examples of heat conductors. A conductor, let's do this as RA, would be any metal. So here they've got listed as stainless steel. And this says fine ceramics, but I'm going to use copper. Copper is a really common conductor. And a conductor, when they say heat conductor, would also be an electrical conductor. And here an insulator you could say a real common one is air. And really any fabric, I'm going to say wool. I feel like we've answered this already. What is the reason hot air balloons rise in the air? It's because the air is heated becomes less dense and through convection the balloon rises. Okay, what is happening in this picture as the ice cream melts? Hint, heat flows from temperature to what temperature? So you can't tell if this is ice cream, but when you look on yours, the ice cream, remember the heat always goes from, heat travels from something that is more hot to cold. So the air temperature here is going to the ice cream. The warm air is transferring thermal energy to the ice cream, and therefore it melts. Okay.